Great. So, does anybody have any questions? All right, so last time we talked about symplectic reduction, and there's sort of at least one more topic about that I wanted to make sure we covered, because, you know, this is originally something inspired by quantum mechanics, not quantum mechanics, classical mechanics. So how do we interpret symplectic reduction in the world of classical mechanics? So classical mechanics, from our perspective, means that you have a Hamiltonian system. You have a symplectic manifold, and you have a preferred function on it called the Hamiltonian, which, you know, in the world of physics would be the phase space and the total energy function. And now imagine you have a Hamiltonian G action on this system. So what do I mean by on this system? I mean that it acts on the symplectic manifold. It's a Hamiltonian action in the usual sense, and it preserves H. I mean that H is G invariant. This has a natural interpretation in terms of Poisson bracket, right? So something preserves H if and only this action preserves H for a connected group, if and only if the Poisson bracket of all of the components of the moment map with H is 0. So I could write the Poisson bracket of the moment map with H, but then you would have to worry about what it means to take a Poisson bracket with a function valued in a vector space. So whenever I take any of the components of the moment map, and really, I mean, the sort of the whole moment map is a conserved quantity for this system. So, you know, the kind of thing you should have in mind is conservation of momentum, this sort of stuff. All right. Yeah, also conservation of angular momentum, again, in situations where that Poisson commutes with H, right? So one nice way to think about this is it tells you exactly when something like linear momentum or angular momentum is conserved exactly when it has trivial Poisson bracket with the Hamiltonian. Oh, I'm not sure.
Sorry, are you sharing the screen? Or because
no, I meant to. Okay, so sorry.
Yep, there we go. Thank you.
Yeah, I haven't said anything too detailed yet, but this is basically what I've said thus far. All right, setting a tone for today. So what does this mean? The fact that the moment map Poisson commutes with the Hamiltonian means that time evolution in this physical system, which is, you know, integrating the Hamiltonian vector field. So the level sets of the moment map are invariant under time evolution in this physical system, and that time evolution commutes with the G action, right? Again, because H commutes with the G action, so its Hamiltonian vector field commutes with the G action. All right, so this shows that we can produce a reduced Hamiltonian system. So you can, let me just remind you what I mean by this. So here, M red is going to be mu inverse of 0 mod G. The induced symplectic form. And then H red is just going to be, well, I take H, I restrict it to mu inverse of 0, and then because it's G invariant, it induces a function downstairs. And I can look at trajectories in this reduced Hamiltonian system. So using my new symplectic form and my new Hamiltonian, I can compute trajectories, and it will match those from the original dynamical system. So my trajectories are going to stay inside the zero moment map level. And if I use the Hamiltonian vector field upstairs to evolve and then apply the quotient map down, that's with respect to the reduced system. All right. So, for example, just to kind of give you a little bit of a feel for how this works, let's do a really simple example. So I have two objects that are moving around in R3, the sun and the earth, for example. And there's a symmetry of this system. Let's assume that I'm using the usual gravitational potential. Well, that only depends on the distance between the 2 points. So if I simultaneously translate them, that's not going to change the energy, right? It won't change the kinetic energy, and it won't change the potential energy because that only depends on the distance. So there's a simultaneous translation by R3, that's a smooth R3 with its action by addition. So the moment map in this case is going to be the sum of the two momenta. So I'm using kind of an important principle, which I maybe referred to but didn't explicitly say, which is if I have two different Hamiltonian actions of G on two different symplectic manifolds, then actually I have a diagonal action of G on M1 times M2, which also has an induced symplectic form, pull back by first projection omega 1, pull back by second projection omega 2. And you'll note when we were talking about Lagrangian submanifolds and symplectomorphisms, I did this with sticking in a sign here. I'm not sticking in that sign, though I could account for that if I wanted to. That has a moment map given by mu1 plus mu2. I'm going to G. You can work this out. It's not hard. I'll leave it as an exercise to you, but it's a very useful thing to note in computing moment maps for various interesting situations, right? So in particular, this is telling us that if we look at the simultaneous translation by R3, we get the sum of the two momenta. The sum of the momentum of the Earth and of the sun is the moment. So what does reduction mean? Well, reduction means we fix what the sum of the momentum is. If you want to be very fancy, right, you have to use this thing about, well, I only talked about reduction at 0. I can take a moment map, I can subtract lambda from it. And so what used to be the preimage of lambda is now the preimage of 0 with respect to this new moment map. I'm not going to kind of write that out. I'm just saying for R3, because it's abelian and the co-adjoint action is trivial, I can just take the preimage of any point in the dual abelian algebra. So I can fix the total momentum of the Earth and the sun. And then I mod out by translation, which, usually people would say, well, I move the center of mass to the origin of the system, right? So what's happening here is the center of mass of the sun and the Earth satisfies Newton's equations on its own. It behaves like a point object. So if I look at how the center of mass changes over time, that just moves in a straight line with whatever the momentum is. So that's kind of a boring part of the mechanics, and I should just get rid of All right, so yeah, as I say, just being a little more careful here, let x1 and x2 be, remember, these are vectors in R3. Which are the positions of my two bodies. I'll just probably keep saying the sun and the earth because that's a little easier to say. And these guys also have momentum. All right, and as I said, I'm going to use standard gravitational potential. So the Hamiltonian here is there's a contribution from the kinetic energy of the sun and the kinetic energy of the earth, which is the respective momenta squared divided by 2m1 and 2m2, the two different masses. And then there's this gravitational potential energy term here. So doing symplectic reduction means we restrict to this moment map level and we mod out by simultaneous translation by R3. All right. So the thing I'm actually interested in is what some people call the displacement vector. What's the, how is this vector going to evolve over time? Right? This is kind of the question, like, you know, I'm interested in, I have the sun and the earth. What's the distance between them going to be? How is that going to change over time? That's one of the coordinates on my reduced space. Again, this is a vector, so it's really 3 coordinates. But even though that's the thing I'm interested in, I'm doing Hamiltonian mechanics, so I have to think in the phase space, and I need to have some kind of dual coordinate. I'm going to need to fix that, but I'll fix that in a moment. Now, I'm sure I could kind of give you a more detailed explanation of why this is exactly the right thing. But let me try to give you some kind of explanation of what's going on in this formula. So, of course, velocity of the sun. And P2 divided by M2, that's the velocity of the Earth. So this expression here is the relative velocity of them, just the derivative with respect to time of the position of the difference between the positions of the Earth and the sun. However, I don't want to use that as my momentum coordinate. And we see why in this equation below. I didn't write this out as I should have. Let me be a little more careful about this. The reason that this equation is kind of bad is I'm taking two vector valued things and taking their Poisson bracket. So it's wrong of me to write a number at the end. But when I do this reduced world, I can still compute Poisson brackets exactly the way I did before. So let me remove this and sort of say, you know, Poisson brackets for R3 invariant functions are the same as before. So there's something a little subtle happening here, right? I want to compute Poisson brackets of functions on the reduced phase space, because that's sort of a good way to get a handle on what's down there, right? And I can do that by taking the functions down on the reduced phase space. I can pull those back to give me R3 invariant functions on the moment map level. And you might say, wait a second, but you're only getting functions on the moment map level and not on the whole space. And there's a theorem that I can extend those to the whole space in any way I want. And the computation of the Poisson bracket on the moment map level will be correct, will be independent of how I choose that extension. And this has to do with the moment map level being coisotropic. Okay, so same as before. So in particular, I can still use the computation that if I take one of the components of xi and pi. So in part, what I had written there was wrong because I wasn't accounting for the fact that there are three components. I could be lazy and assume that my Earth and Sun are moving in a one-dimensional world, and it wouldn't really change this computation, but let me be a tiny bit careful for the sake of realism. So x2i, p2. So this is just saying that the position and momentum observables of the sun are conjugate, canonically conjugate. They have this Poisson bracket relation of I take the Poisson bracket and I get the delta function, same here. And then if I take the Poisson bracket of a position of the sun and a momentum of the Earth, or any observable about the Earth and any observable about the sun, the Poisson bracket is 0. So if I take the Poisson bracket of anything involving, this is kind of a pain to write out, x1, x2, or x1, p2, or p1, x2, or p1, p2, all of these are 0. Sorry, my iPad is being very slow. I don't know why it's having so much trouble when I'm on the call. That seems to be the only time that it has this issue. So if I look at x1, 1 minus x2, 1, and I take the Poisson bracket of that with the velocity, the relative velocity between these two bodies, I don't get the sort of canonical relations I want, right? I get, well, the x1 with p1 gives me 1, so I get 1 plus, so there's a minus sign here and a minus sign here, so I get plus 1 over m2. Oops. And just note for the sake of completeness later that 1 over m1 plus 1 over m2 is m1 times m2 divided by, this is the reciprocal of 1 over m1 plus 1 over m2. And this quantity is what's called the reduced mass.
Can I ask a question?
Yeah, of course.
I'm just one because if we think about two bodies and 2 point-like particles, for example, then we can't, they can't meet together. They can't be in the same point, right? So typically we also have to take out the diagonals.
Mm-hmm.
So when you said that we can extend the, the Poisson bracket to the entire space is that also true when we take out the diagonal?
Yeah, I admit I'm being lazy here about points like that. I mean, if you look, right, my Hamiltonian function blows up when x1 equals x2.
Mm-hmm.
So yes, I really shouldn't be saying, I should be saying like, yeah, T star of, says R3 times R3 minus the diagonal. So yeah, and then the reduced space is T star of R3 minus the origin.
Mm-hmm. Yep.
Right, and exactly what I want to be careful about here is, from the perspective of topology, it's very easy to see that the reduced space is T star R3 minus the origin. But you have to be careful about getting that right symplectically.
Right.
The canonical symplectic form on the cotangent bundle. So if I use x1 minus x2 as my coordinate downstairs, what's the right coordinate to use on the cotangent line that gives you the canonical symplectic form on this cotangent bundle? So that's sort of the computation I'm doing.
Okay.
But yes, you're right that I need to be careful about that blowing up, because
thank you.
My H just isn't defined there. So okay, great. But that doesn't change anything about these computations, because if you do computations on an open set, that's the same as doing it on the whole thing. All right. So yes, when I sort of think about, well, is the relative velocity a good cotangent coordinate to use? I see, oh, no, it isn't. It doesn't give me the canonical symplectic form. It gives me the canonical symplectic form up to this weird scalar factor. So, the right cotangent coordinate, yeah, okay. Is this guy, and I won't write it a second time. So it's the velocity times the reduced mass. That's sort of the right kind of momentum to use. And it's a sort of long observed principle in celestial mechanics that when in this two-body problem, the displacement sort of behaves like an object whose mass is this reduced mass m1 times m2 divided by the sum of the two. And one way to think about that is, oh, well, that's, it's behaving like something whose momentum is velocity times this funny scalar that shows up. Okay. And another way to see that this is kind of the right thing to do is if you rewrite the Hamiltonian function using this coordinate p twiddle, I won't go through the algebra, you substitute it in, you expand stuff out, what you find is exactly you get energy function where, so this is the length of this, you could call it reduced momentum squared times 1 over the reduced mass. So again, the kinetic energy behaving as though the displacement were an object with that mass, plus this term, which is the kinetic energy of the center of mass. So this lambda, we fix that to be the sum of the two momenta. So it's behaving like this is the kinetic energy of if you smush the two things together and had them sit at their center of mass. It would have mass m1 plus m2, and lambda would be its momentum. All right, and then the gravitational potential energy stays exactly the same. That doesn't depend on the momentum. So looking at the symplectic geometry, trying to get this cotangent bundle expression right, immediately sends us to the right formula for the Hamiltonian here, and makes it a relatively easy system to solve. Now I'm already 30 minutes into the class, so I think I did make the right decision to not try to also write out what would happen if I tried to reduce with respect to SO3, but I could do that. And I'll just note there you have to be more careful because SO3 is a non-abelian group, right? So if the angular momentum is not zero, you can't just divide out by SO3 because acting by SO3 will change the angular momentum. And so you instead have to fix the angular momentum to just have a particular norm, whatever it is, that won't change. In fact, that gives you one of the co-adjoint orbits of SO3. And then you can divide out not by all of SO3, but by the circle that preserves the angular momentum. So you can reduce somewhat, but not as much as with R3. Yeah, that's life. All right. Are there any questions about this story? All right, this is again, just to kind of give you a flavor of, you actually can learn things about actual classical mechanics using reduction. You can use a symmetry of your system to go down to a reduced system and see some features of the behavior on a lower dimensional manifold, right? Rather, here, rather than thinking about a 12-dimensional phase space, you're thinking about a 6-dimensional phase space, etc. All right. So I wanted to, that was sort of stuff I hoped to cover last time. Kind of knew last time was probably a little too much for one lecture. That might happen again here, we'll see. But I wanted to talk about kind of one other interesting example of a moment map in symplectic reduction, which I think Canis Silva includes, and which I think is an interesting inclusion. And let me say some tiny amount of words about this. So yeah, to give you some kind of general context, yeah, well, actually, no. I would like to give you general context, but I think I should actually explain what the words involved mean, and then the context will make much more sense. So what I want to talk about, this chapter in Canis de Silva is called the moment map and gauge theory. So it's about sort of a construction inspired by physics, where you actually have an infinite dimensional Lie group acting on something interesting, infinite dimensional moment map action. So the underlying context is going to be of principal bundles. So this is on one hand a little bit of a sidetrack from what we've been covering, but on the other hand, sometimes you need to introduce objects to be able to talk about interesting examples. And principal bundles are something worth understanding on their own. So I apologize to those of you who already understand principal bundles. The next 20 minutes might be kind of boring for you, but I think these are actually kind of important ideas. They're worth kind of going through and lit up in your mind. I don't know. I had to see connections explained like 4 different times in 4 different contexts before I actually understood what the hell was going on with them. So I'm a little biased toward thinking like, oh, probably people need connections explained to them, because somehow for me it was very hard to wrap my mind around. So, okay, in case you don't know, a principal bundle, what this means is I have some base, which I'll call B throughout. And a principal bundle is space mapping down onto B such that every fiber looks like a Lie group I fixed beforehand. So it's a manifold where I have a free, smooth G action. So not only does every fiber look like G, I have a G action that looks like left or right translation, depending on how you set things up. Action, so I'll say left translation, such that this base is what happens when I get the quotient. It's the orbit space of that action. So I have a manifold, it has a free smooth G action. It has a map down to another manifold B, which is the orbit space for the G action. And this map is the thing that sends each orbit to the equivalence class. And I want this to be locally trivial. So it should be kind of locally modeled on, I have some open subset down in the base. As long as it's small enough, its preimage is just going to look like that open subset times G. And the G action is going to just be left multiplication on the second and leave the first factor alone. So the easy way to come up with one of these is to just take the trivial one. Example, I can just take G times B, let G act on the first factor by left multiplication, and this will, for sort of stupid reasons, be locally trivial. Yes, Josh.
Is the action assumed to be transitive on the fibers?
Yes, that's implied by the fact that B is the space of orbits.
Okay.
And it's also implied modeled on this product, right? So any question about a single fiber, I can answer by looking at actually just the trivial principal bundle. I take my base space and I multiply it by G. All right, so yeah, what's going on here is every fiber is isomorphic to G, but not canonical. So for every fiber, if I choose a base point in the fiber, then acting on that with the group will give a bijection between my group and G. And actually, in this case, because I'm working in the smooth category, and a diffeomorphism between the two. But there are also non-trivial examples out there. So Canis de Silva mentions one is if I look at S3 inside C2, then I have an action of S1 by multiplication by unit complex numbers. So that's a free G action. So if I just mod out by it, I can think of that as a principal bundle over the quotient. So in this case, the quotient is actually S2, CP1. And obviously S3 is not S2 times S1. So this is kind of the first example of a non-trivial principal bundle you should have in mind, but there are many, many more examples. Another kind of important source of these for us is if I have a Hamiltonian G space, and G is compact, and X freely on the moment map level, then the moment map level mapping down to the symplectic reduction is a principal bundle.
I have a question.
Mm-hmm.
Is it easy to give an example of something that would fail the local triviality condition?
Oh, like something which yeah, I would need to think about that one.
Okay, that's fine.
So, part of what's going on here is I'm talking about smooth manifolds. I mean, this makes sense in a much more general context, right? And if you're on a smooth manifold and the map from P to B is a submersion, then the local triviality is automatic.
Okay.
So, somehow like you would have to come up with some situation where that didn't work.
Okay.
So yeah, I mean, I'm sure I could. So you could do something dumb like, so the standard example of messing up your, I'm not absolutely sure what the right way to do this is. I was sort of thinking that I could somehow use like one of these examples of a map which is bijection but not a diffeomorphism, right? Like
Okay.
x cubed from R to R is bijective, but it's not a diffeomorphism. Its derivative at 0 is 0.
Right.
And so like that's the sort of thing I would worry about.
Okay.
So somehow in practice, this very rarely happens, but this just lets you avoid any such concerns.
All right.
So in another context, there are other things in mind is if B and P already have manifold structures, and the map from B to P is the derivative is surjective, then you can basically use the implicit function theorem to get this local triviality.
Okay, thanks.
All right, cool. Okay, so yeah, that's another interesting example. And in fact, this S3 example is such a thing. It's from the moment map, the Hamiltonian action of S1 on C2. So this is actually a pretty big class of interesting examples coming from these symplectic reductions. The end of the examples. So although one way to think about this local triviality is actually that there needs to locally be a section. So if I have a section of my principal bundle, then by using the free G action, I can trivialize it. Basically, I can send U, comma, the identity to my chosen section, and then G, comma, U goes to G acting on that guy. All right. And so actually an observation which commonly comes out of this is a principal bundle is trivial if and only if it has a section. If you have a section of a principal bundle, you can use that to trivialize the principal bundle. So this might sound like kind of a strange notion if you've never encountered it, a little kind of odd, but actually it's a really important notion in geometry. And the reason is that principal bundles control all other kinds of bundles. So Kenneth de Silva doesn't really explain this, but I think it's actually a really important idea. So I wanted to at least say a little bit about it. So the kind of bundle you're probably much more likely to be familiar with is a vector bundle, right? So that's a map from one manifold to another manifold. Kind of superficially looks like this principal bundle, but it's a little bit different. The fibers of the map each have a vector space structure, and locally it's trivial compatibly with the vector space structure, right? So I have an isomorphism of pi inverse of u with u times Rn, which preserves the fiber with the vector space structure on Rn. Now, if I look at a vector bundle and I look at two open subsets with some overlap, well, and over these two subsets, I have two different trivializations, which I'll call phi1 and phi2. Then, well, I can look at the overlap, u1 intersect u2, right? I can look at that times Rn, and I can take the inverse of one of these and then apply the other one. And what that gives me is, well, for every element in the overlap, I get a matrix, which is the map from Rn to Rn, induced by undoing one trivialization and then doing the other one. And if you think about this a little bit, you can reconstruct the vector bundle from these functions, right? If you take an open cover of your manifold with where you can find trivializations of the vector bundle, then you can rebuild the vector bundle by starting with the trivial vector bundle on each one of those patches and then using these functions to glue them together. So all of the information of the vector bundle is actually bound up in these transition functions. And you can just use the same transition functions to build a GLNR principal bundle instead. If you don't like this kind of pick and open picture, you can think about this more abstractly as I look at the space, which is a point in the base of my vector bundle, and an isomorphism from Rn to the fiber of the vector bundle. So that has a GLNR action by pre-composition. I act with GLNR on Rn, and that gives me a different isomorphism. That is free and transitive on each fiber because, well, if I have an isomorphism from Rn to another vector space, pre-composing with GLNR acts freely and transitively on the set of such isomorphisms. So again, this is a situation where you get something which is isomorphic to GLN, but not canonically so. I have to choose an isomorphism first before I can think of all the other isomorphisms as GLNR, elements of GLNR times that isomorphism. All right. So actually, I could never talk about vector bundles, and I could think about GLNR principal bundles instead. And more generally, for any kind of fiber bundle, kind of the information you need is, well, I need some model space that every fiber is going to be isomorphic to. And I can also sort of want to say, how unique is that isomorphism? Which, if you think about it, is specifying a set of allowable automorphisms of the fiber. So a fiber bundle always has some trivialization. The fiber is isomorphic to some model space. And I have to think, oh, well, if I do this trivialization in two different ways, what kind of automorphisms of the model by two isomorphisms to differ by? So in order to have a linear space, you should allow GLNR and only things in GLNR, because that sort of specifies the linear space structure. All right. So for any other kind of fiber bundle, well, there's some other group, which is the allowable automorphisms of the fiber. And you can essentially just replace your fiber bundle with a principal bundle for that structure group. So for example, if you're interested in a vector bundle with an inner product, well, you look at the automorphisms of a linear space with an inner product. So it's an ON principal bundle. And again, you could, write it in these terms as, I have a fiber and I have an isometry from Rn to my fiber preserving this inner product. If I have an SLN bundle, the volume form, by which I mean a top form, your vector bundle. If you want to start with a real vector bundle and think about preserving a complex structure on it, I should maybe say almost complex structure because I'm not thinking about any kind of integrability, then you want a GLNC principal bundle, et cetera, et cetera. So kind of every notion you might think of a fiber bundle with some extra structure is always going to have this structure. So the language of principal bundles lets us think about all of these in a totally consistent way, where the only information you have to put in about what kind of fiber bundle you're thinking about is what its allowable automorphisms are. Are there any questions? Well, as I say, this is a little bit of a tangent, but it's genuinely interesting stuff.
I have a question.
Sorry.
What about the converse? I mean, if I have, so you've just said that from a vector bundle, I can get a GLN principal bundle. Does it go the other way as well?
Yes. So since I'm going to use this notion a few times going forward, let me actually write it out properly. Given a principal G bundle, P and any space X with an action of G, then I can construct what's called the associated bundle. So the associated bundle is, I didn't give myself enough space. I look at X cross P and I mod out by the action of G, the diagonal action of G. And that has a map down to B, which is take your point in P and look at what its image is in B. And this is one, so this allows you to construct a vector bundle by looking at GLN acting on Rn and taking this associated bundle for it. And I mean, there's even sort of a reconstruction theorem of like a principal bundle for, let's just say a Lie group for now. I don't know exactly how general this is. For Lie group G is the same thing as a functor from its category of representations. The vector bundles satisfies such and such properties. So yeah. So you can do a similar thing with ON or SLN acting on Rn, and precisely because ON preserves an inner product on Rn, the corresponding vector bundle also has an inner product. So yeah, I'm going to use this notion a few times, so good to just put it out there explicitly. All right, any questions? I think I'm going to take a quick break. We'll be back in a moment. Okay, I'm back. So, anybody have any questions? Okay, great. So, as I say, the powerful thing about principal bundles is it lets us think kind of uniformly about all of these kind of situations. So one really important structure we'll talk about is connections. And you could imagine saying, okay, here's the right notion of a connection for a vector bundle with a fixed top form. Here's the right notion of a connection for a vector bundle with an inner product. Here's the right connection of a vector bundle with a symplectic form on each of its fibers, right? And you can sort of say, well, wait a second. We should be able to phrase this in a sort of uniform way using the fact that all of those are really secretly principal bundles. So what is a connection? A connection in a bundle, in particular a principal bundle, but it could be some other kind of bundle, is a rule for lifting paths down in the base up to the total space, having fixed a pre-image of one of the endpoints. So the sort of picture to have in mind here is I have a path down in my base. I pick an element of the fiber over one of the endpoints, and the connection tells me a way, sort of consistently, of lifting that path up into a path in the total space. So you'll hear this phrased in slightly different ways, right? By looking at the other endpoint of this path, this endpoint is B and this endpoint is B prime, then we get an identification of the fiber. Let me write this properly. We get a map from the fiber over B to the fiber over B prime. So you might hear this called parallel transport, this sort of idea of I have some extra structure sitting on my manifold and I want to move that around. So for vector bundles, say with some extra structure, this map should be linear and it should preserve that structure. For a principal bundle, the right notion of preserving structure is that it needs to be G. So again, sort of somehow all of this kind of what kind of structure do you want to preserve on the fiber, it all just gets wrapped up in the group action. So that's sort of the moral definition, but that's not usually how you'll see them actually defined. So what you'll see more often, one sort of approach is what is often called the Aeroslung connection, which is, okay, think about that description, but think about what happens infinitesimally now, right? I have some path down in B. It has a tangent vector that's giving me the velocity at 0. And I choose some pre-image, and now I have a lifted path upstairs, and that also has some tangent vector, giving the derivative at 0. And I get a linear map of the original path to the derivative of the lifted path. So that's a linear map from the tangent space of B at the point downstairs to the tangent space of P at the point upstairs. And that's a splitting of the derivative of the projection map. So it's a map such that when I project back down, I get the identity. By G equivariance, this has to be a G equivariant map. So if I choose some other pre-image, well, I got to that other pre-image by acting by some element of the group, and everything has to be compatible. with taking the derivative of action by that element of the group. So I mentioned this before, but it never hurts to be reminded, right? There are a bunch of different ways to think exact sequence of vector spaces. So what's happening here is I have a short exact sequence of vector spaces given by, here's the kernel of the projection, the derivative of the projection. This is often called the vertical space, because we sort of imagine this picture here with the fiber being vertical and we're projecting downward. That maps into the tangent space of the principal bundle, and then that maps to the tangent space of B. All right, and I'm splitting the short exact sequence. Whoops, that doesn't go there. So another way, splitting in the sense of choosing a map back like this, such that the composition going around this way is the identity. All right, well, equivalently, we could think of that as choosing a complement to the vertical space inside the tangent space to the principal bundle at P, which of course we unimaginatively call the horizontal space. So, what's happening here is we're choosing for each vector downstairs what the horizontal vector lying above it is. So this vertical space, that's a canonical thing. It's the derivative, the kernel of the derivative of the projection map. It's just all the vectors that push forward to 0, or another way to say this is all the ones tangent to the fiber. But there's no canonical complement to that. There's no canonical horizontal things. That would be a section. And if your principal bundle isn't trivial, there's no choice of a section. So this is just extra information, and that's the information of the connection. And the property this has is, well, like I said, it's complementary to this vertical space. Again, it's called V of B. And it's invariant, it's equivariant with respect to G. So when I act by an element of G, I can take the derivative of that. That induces a map on tangent spaces. That should send horizontal vectors to horizontal vectors. And this is the definition of an Aeroslung connection. And it sounds pretty simple when you put it like that. I don't know why it took me so long to figure out how connections work. But, well, as you see, there are a lot of different ways of thinking about them. So different people will present them in different ways, and well, different ones will work differently. So there's another way of thinking about splitting of a sequence of vector spaces. If I have a map like this, I can equivalently think about the splitting map going back this way with the property that going around this loop is the identity. And that's the same as choosing HP inside here. So I can rewrite my connection in terms of a map from the whole tangent space to P to this vertical space. And well, what's that vertical space? The group G acts at each point. And having chosen a point, I get an isomorphism to G. So actually, that vertical space I can think of as the Lie algebra. There's a map from G to P, which sends G to G times my point P. So of course the identity maps to P, and when I take the derivative, I get an induced map from the Lie algebra to the tangent space of the principal bundle. All right, so I get a map from the tangent space to G. So people will call that a Lie algebra valued one form. G value. And of course, it's got to be a splitting. So its kernel is going to give me this horizontal space. And when I restrict it to vertical things, I get the identity. So yeah, this gives me a G valued 1 form, which we are going to denote capital A. And you'll often see 1 forms defined, connections defined as these 1 forms, but somehow, at least for me, if you don't already understand this Aeroslung definition, it seems very confusing. Yeah. All right. So there's sort of one basic property of connections we're going to need to talk about, which is their curvature. This is sort of the basic thing to look for in a connection is what is its curvature. And that's a measure how this changes when you vary the curve gamma. So let me go back to my original lift. If I vary my curve gamma, then this curve might change. And in particular, it might not close back up. I might change what my endpoint is. I might change the map. And that's sort of what curvature is detecting. To write that out sort of, again, in a more kind of compact way, we want to think about, well, how do we kind of think about this infinitesimally? How do we see how kind of very close to 1 point these lifts change? How do we think about that in terms of this lift vector fields? Well, the answer is somehow the way to think about like varying our path a little bit fields and to think about flowing with them in the opposite order. So I can flow with respect to X and then with respect to Y. I can flow with Y with respect to X. I get different answers, and the Lie bracket exactly measures the difference between them, right? Now, on the other hand, I can take this picture and I can lift that up into my principal bundle. So I can flow by the horizontal lift, which, you know, that's what L is, of X. I can flow with respect to the horizontal lift of Y. I can flow with respect to the other ones. Again, that might not close up. Well, there's some amount of not closing up which comes from the base. That comes from the Lie bracket of the 2 vector fields. So I also take lift of that Lie bracket. But even still, that might not close up. I might be kind of getting something where there's something interesting happening along the vertical direction. So this is the kind of picture to have in mind for what curvature means. So curvature is actually going to be a G-valued 2 form, where what we do is we take the Lie derivative, the Lie bracket of the lift of 2, oh, oops, I wrote the wrong thing there, the lift of 2 vector fields, and we compare that with the lift of the Lie bracket itself. Right, so exactly what's happening here is this right-hand term, the left-hand term corresponds to going around this way, and the right-hand term corresponds to going this way. Essentially closes up downstairs by definition, or it gets closer and closer to being closed as you flow less and less by X and Y. Whereas up here, you do this 2 same things, but they don't end up closing up. Instead, you get some difference along the fiber. So this is a G-valued 2 form because this guy is vertical. All right, Canis de Silva actually defines curvature differently. In Canis de Silva's definition, what you have to do is take the exterior derivative of A and look at what that does only on horizontal vectors. And if you sort of look at the definition of the exterior derivative, you'll see that actually what she's asking you to compute is exactly this difference between the Lie bracket of the lifts and the lift of the Lie brackets. But I find this definition much easier to understand what the heck is going on. I'll just mention you'll also sometimes see the definition curve A equals dA minus A wedge A. Has the annoying property that you have to explain what A wedge A is. So Canis de Silva does tell you, kind of at least implicitly tell you this, that the exterior derivative applied to vertical vectors has a kind of universal expression in terms of the Lie bracket on our Lie algebra, which is the same for all connections and is expressed by this A wedge A. And so this expression is basically just taking the exterior derivative, taking off the part that comes from vertical vectors, and so only leaving what you get for horizontal vectors. Whew. All right. So what does this have to do with symplectic geometry? I've got 15 minutes to try to kind of wrap this up. And the answer is, before I try to write things out, the space of all connections on a two manifold, so I'm only considering compact two manifolds for now, actually is a symplectic manifold. And the curvature is the moment map for a particular group action on this. So we'll need to think a little bit about what group the curvature could be a moment map for. But this is sort of, at least to me, a kind of pretty surprising fact. So yeah, we're going to restrict to the case where B is a smooth two manifold. I always hesitate to say surface because people are used to thinking about algebraic geometry. We'll think of them as curves, so it's easier to just say two manifold. And G is going to be a Lie group. It doesn't have to be compact, though that's a nice case. The answer is that it should have an invariant metric, which is the same as saying there's an inner product on the Lie algebra, which is invariant under the adjoint action. Inner prod G invariant under add. And that's always possible if your group is compact. It's compact or semi-simple. Okay. So if your group is semi-simple, that's given by the killing form. And if your group is compact, then you're semi-simple plus some torus part. So you can just choose something on the torus part and use the killing form on the semi-simple part. All right. So the space of connections, sort of funny. It's an infinite dimensional affine space. It's not a vector space because you can't add two connections and get a connection. But if you take the difference between any two connections, so if you're thinking about this in terms of these forms, right, the difference of two connections, you're going to have that the restriction to the vertical part is 0. Yeah, and the kernel contains HP. If you got what the difference is, an easy way to say this is it's hum from the horizontal space to the vertical space. If you want to think about this downstairs on B, you can think of it as a one form, and it's going to be valued in one of these associated bundles. So you take the principal bundle and you look at the associated bundle for the adjoint representation of G. This is a useful thing to think about because this corresponds to G invariant stuff upstairs. So i.e. a G invariant G valued one form. That vertical vector. I should have said G valued one form, which is horizontal. So I think sort of think of it as a bit nicer to think of it as something down on B, but Kenneth de Silva always avoids doing this because she never wants to talk about associated bundles. She sort of is always hiding them, which, you know, fair enough, but I really like associated bundles, so I don't want to hide them. So this means that the tangent space to the space of all connections at any point, it's an affine space. So if I want to kind of move in any direction, well, I just add a kind of infinitesimally small one form of this type. So either you can think of that as a section of the cotangent bundle insert with this associated adjoint bundle, or as a horizontal one form that's G invariant and G valued upstairs, which is just kind of a fancy way of writing sections of this bundle. Because of the metric, we have a pairing on the Lie algebra, which we can also think of as a pairing on the associated bundle because the inner product is G invariant. So if we have two of these one forms, we can consider the wedge. Now, this is a little bit weird because these aren't valued in numbers anymore. They're valued in this Lie algebra. So the wedge is actually valued in the tensor product of the Lie algebra with itself. So it's AX tensor BY and AY minus AY tensor BX. But this is only kind of an intermediate thing, so don't let that worry you too much. We're going to now apply this inner product. So I'm getting the R valued 2 form where I take AX paired with BY minus AY paired with BX. So that takes in two horizontal vectors, so two vectors in the tangent space to B, and it spits out a number. And it does that in a way that's anti-symmetric, as you can read off from this formula. So that's a 2 form. If you're thinking of it upstairs on P, it's G invariant. Now we're just talking about numbers. So it's really just the pullback of a 2 form from the base. We can define the symplectic pairing of two of these one forms, A and B, as construct this funny wedge and then integrate it over the surface. And it's a 2 form, so it really makes sense to just say integrate it over the surface. Right? A 2 form is by definition something that we can just integrate. We don't have to make any choice of measure or anything like that. All right. So this makes this tangent space into an infinite dimensional symplectic vector space. You need to check that this is non-degenerate. And I'll just note here, of course, I'm being not very careful about infinite dimensional vector spaces and completing and all of this stuff. Don't worry too much. I mean, if you want to write a paper about it, worry about that stuff. But for now, given that I only have 10 minutes left, so that makes the space of connections into an infinite dimensional symplectic manifold. And fair enough. It's a cool observation, but what are you going to do? How are you going to actually use the symplectic geometry we've learned in this situation? Well, as I say, we're actually going to think of curvature as a moment. So A has a natural action of infinite dimensional Lie group called gauge transformations. So gauge transformation, that's a map from P to P that commutes with the action of G, and it preserves the map from the principal bundle down to B. For a trivial bundle, it's useful to think about this. On a trivial bundle, this is just maps from the base into G. We'll act on the trivial principal bundle by inverse rate multiplication. So I have F, a map from B to G. How does that act on a pair B comma G prime? Well, I take B G prime times F of B inverse. And why do I do the F of B inverse? So that I get a left action that commutes with the left translation by G. And for general P, you can write this down. It's sections of some associated bundle where the group acts on itself by the conjugation action, and you get an associated bundle from that. You can take sections of that. So let G be the gauge group, the group of gauge transformation. Ooh. Ooh. And I should say, you should think of this as kind of a set of coordinate changes, right? It's a way of kind of changing exactly what we think of kind of rotating the fibers upstairs without changing anything about what's happening downstairs. So it's sort of exactly the things where you can't see anything about what changed downstairs. Of this guy is sections of this adjoint bundle, right? It's G-valued functions on the principal bundle P, which are G invariant. So Lie algebra valued functions invariant under the group, that's actually sections of this adjoint associated bundle. And the dual, well, I want something I can pair with one of these Lie algebra valued functions and get a number out at the end. So that should actually be two forms valued in the same vector bundle, because then I can pair two of these guys and get real valued two form on B, which I can then integrate. So again, you have to be a little bit careful about what I mean here. I certainly don't mean the full vector space dual, but that's a vector space with a natural pairing. So I can think of curvature as actually mapping from the space of connections into the dual of this Lie algebra. And it's theorem of Atiyah and Bott that actually the action of the gauge group on the space of connections is Hamiltonian with moment map given by the curvature. So I'm just writing out here what the definition of moment map is. So if I look at the curvature paired with the adjoint bundle, again, I'm going to pair those together. I get a real valued 2 form. I can integrate that over the surface, and that's the same as, and then I can take the derivative of that in the space of connections. So one of the things that's tricky to keep track of is where are you taking derivatives here? This is a function from the space of connections to the real numbers, and you can take the derivative of that on the space of connections. Take its exterior derivative, and that should be the same as taking this element of the Lie algebra and pairing that, contracting the symplectic form against it. And through that argument, I'll sort of decide whether I should do it on Monday, but you can look in Canis Silva, somehow once you understand this for S1, it's not really too bad to extend it to general groups. And if you go through S1, at the end of the day, it's integration by parts. That these two guys exactly end up being, well, you can interpret both of them as some integral over the surface, and they're equal because of integration by parts. Which just seems to always come up. It's one of those things. So what I'd rather spend, the 2 minutes I have left on is thinking about, okay, what does this tell us? What good is this? Well, we know what to do with Hamiltonian actions now. You should take their moment map level. So look at the connections which have curvature 0, flat connections. And now mod out by gauge equivalence. So look at the moment map level, mod out by the group. And it turns out this is actually a finite dimensional symplectic manifold. And it's a very interesting one. There's lots of work trying to understand its topology, how it behaves. Let me just say there's sort of another way to think about this. A flat connection exactly means that when I continuously vary what the path is without changing the endpoints, I will get a map which is unchanged. So flat exactly implies that the map here, the lifted map from fiber over one thing to fiber over another point only depends on the homotopy class of the path. Right? It says that when I do a little deformation of my path, I'm not going to change what the lift is because that would involve integrating the curvature over the surface I'm sweeping in. So in particular, if I look at a single point and I go around some non-trivial element of pi1, I get some element of my group, which is the automorphisms of that fiber, with the action of G. And that only depends on class in pi1. So in fact, this reduced space, which maybe I'll give a name, X. So each point in X gives me a homomorphism from pi1 of X into the group G. And modding out by gauge just means that I look at this homomorphism, and when I act by gauge transformation, I just look at what it is on this point. So this is pi1 with some base point. Transformation does is it conjugates this action by a particular element of the group. And this map is actually a bijection and a diffeomorphism, if you interpret what this is as a manifold correctly. So in particular, if G equals GLN, R, or C for that matter, this is just n-dimensional representations of pi1 of X. Sorry, I shouldn't have written X here. I'm so used to that. It's pi1 of B. Sorry, that's the pi1 in the picture. This is n-dimensional representations of pi1 of B up to isomorphism. This is really kind of a natural geometric space to be thinking about, but this gives us a completely different perspective on it and gives us in particular a symplectic structure on it, which is very non-obvious when you think about it as representations of the group. All right, so I think I'll stop there. Like I said, I'll sort of contemplate whether I should talk more about the case of S1 next time, because it's nice to see the computation, but it's all laid out in Canis de Silva. So if you're sort of curious, you can just read about it there. All right.